Right now, the strongest storm on Earth is locked onto a target. 170,000 Americans. No mainland, no highway out. Just 4 islands, 30-foot seas, and a Category 5 typhoon that has their exact coordinates. That alone should be the story. But while meteorologists were issuing an upgrade to the storm, something else was registering on a completely different set of instruments. A magnitude 5 earthquake, directly beneath the same island chain in the same window of time. 2 systems, 2 sets of data, 1 geography. And when 2 systems are active over the same ground at the same time, you're no longer dealing with a weather event. You're dealing with something we do not have a name for yet. If you genuinely enjoy what I do here, make sure to hit like and subscribe to Project Nightwatch, because this story is not over, and neither is our coverage. Drop a comment telling me where you are watching from and what time it is there. And tell me this: the strongest storm on Earth is bearing down on 170,000 Americans with no evacuation route, and a magnitude 5 earthquake just registered beneath the same islands in the same window of time. 2 systems, 1 geography, nobody connecting them. Do you think that is coincidence or something else? Let me know in the comments. Now, let us get into it. Part 1. The upgrade that redefined the situation. There is no gentle way to begin this. At 9:19 p.m. local time on April 12th, the National Weather Service office in Tian, Guam issued an upgrade that changed everything about the next 48 hours. Super Typhoon Sinlaku had just become a Category 5 storm, and in that moment, it became the strongest storm anywhere on the surface of this planet. Not the strongest storm in the Pacific, not the strongest storm of the season, the strongest storm on Earth, full stop, and it is pointing its eye directly at United States territory. Let's be exact about what that means geographically, because the geography here is not a background detail, it is the entire problem. Guam sits roughly 3,700 miles west-southwest of Hawaii and roughly 1,500 miles east of the Philippines. Saipan, Tinian and Rota are strung out just north of Guam like stepping stones across the western Pacific. Together, these islands are home to approximately 170,000 American citizens. People who carry US passports, who pay into federal programs, who fly the American flag. And right now, not a single one of them can leave. There is no bridge to the mainland. There is no highway to higher ground somewhere else. When a Category 5 typhoon locks onto your island, your options reduce to 2. Shelter in place, or shelter in a better place on the same island. That is the entire menu. The National Weather Service forecast at the time of that upgrade was not subtle. Tropical storm force winds were already on the way. Typhoon force winds, defined as sustained winds of at least 64 knots, were expected to arrive within hours. Seas were building toward 30 feet. The phrase used in the advisory was incredibly dangerous for small craft, which is the kind of clinical understatement that the Weather Service uses when what they really mean is that anything on the water is going to have a very bad time. Flash flooding was in the picture for all 4 major islands. Runoff was expected across entire drainage systems, meaning that even inland areas, even areas that might feel protected from wind, were going to be dealing with water coming from every direction. Now here is a thought experiment that might help recalibrate the scale of this. Imagine a Category 5 hurricane, the kind that makes every meteorologist on television go pale, targeting Key West, Florida. The response would be immediate, enormous, and federally coordinated within hours. Evacuations would be mandatory. The interstate highway system would reverse its lanes. The National Guard would be pre-positioned. Mainland media would have wall-to-wall coverage before the storm even reached hurricane strength. We would be watching, because it would feel close, because it would feel real, because we could see it happening to people who look like the people on the evening news. 170,000 people in the Marianas do not have that buffer of attention. They are thousands of miles away from the cameras and from the evacuation routes. The coverage gap is real, and while I want to be careful not to overstate what is and is not being reported, I will say plainly, the number of outlets giving this storm the same energy they would give a Florida landfall is not proportional to the threat. That disproportionality matters, and we are going to come back to it. But here is the thing. Here is the thing that made me stop when I was pulling the data tonight. At the exact moment that upgrade was being issued, at the exact window in which meteorologists were confirming that this storm had crossed into Category 5 territory, something else was happening. Something underneath. something the storm forecasts do not cover, and the earthquake bulletins do not connect to the typhoon. And when I tell you what it is, I want you to hold both things in your mind at once, because the story of the next 48 hours over those islands is not purely a weather story. It is not purely a geology story. It is something that does not have a clean name yet, and that namelessness is part of why it is so unsettling. Keep that thought. We're going to need it. Part 2. The earthquake nobody is talking about. Within hours of that Category 5 upgrade, the United States Geological Survey registered a magnitude 5.0 earthquake near Pagan Island in the northern Mariana Islands, the same chain. The same arc of volcanic rock rising from the same oceanic trench. Two events, one atmospheric, one geological, occurring in the same narrow corridor of the Western Pacific, in the same narrow window of time. Now, before anything else, let me be straightforward about what that earthquake was and what it was not. Magnitude 5.0. Depth, 226 kilometers. That depth classification matters enormously. We're going to spend real time on it in a later act. But the short version is this. Earthquakes at that depth do not generate tsunamis. The energy dissipates over too much distance and through too much material before it ever reaches the seafloor in a way that would displace surface water. So no tsunami warning was issued, and correctly so. We're not in a situation where we're adding a tsunami to an already terrifying forecast. That is not the story here. The story is more subtle and in some ways more interesting. Pagan Island sits approximately 300 kilometers north of Saipan. It is not a populated island at the moment. It has a complicated evacuation history that we will get into, but it sits on the same geological structure as the rest of the chain. The same string of volcanic islands that are all surface expressions of the same enormous subduction system grinding away underneath. The earthquake beneath Pagan was not an isolated event dropped from nowhere onto a quiet map. The Mariana Arc is one of the most seismically active zones on the planet. Magnitude 4 and Magnitude 5 events happen regularly here. If you pulled up the USGS earthquake feed on any given week and filtered for the Mariana region, you would find a list. This is a place where the ground moves, always. So why does this particular event deserve attention? Because of when it happened. Two timelines overlapping, one above the islands, one below them. And the question that serious researchers in compound hazard analysis would ask, and I want to be clear that I am raising this question, not answering it, is whether two simultaneous extremes produce outcomes that neither extreme would produce alone. Think about what that looks like from the ground. You are on Saipan. The sky above you is tightening. Barometric pressure is dropping in a way you can feel in your ears. The surf is already building. Emergency alerts are active on your phone. You're doing what people do before a major typhoon, taping windows, moving furniture, filling containers with water. And somewhere beneath your feet, at 226 kilometers down in the geological zone where the Pacific plate grinds against the older mantle rock below, the Earth is releasing stress. That earthquake registered. It was real. The ground moved under those islands tonight. Most of the time, a magnitude 5 deep slab earthquake in the Mariana Arc is a footnote. It gets logged, it gets catalogued. Some researcher somewhere adds it to a dataset. Nobody writes about it. But we're not in a normal situation tonight because the ground the earthquake occurred beneath is about to receive a Category 5 typhoon. And those two facts sitting next to each other raise a question that existing emergency planning frameworks are not designed to answer. That question is not, will the earthquake make the typhoon worse? The physics do not connect in that direction. The question is, what happens to saturated ground, to destabilized slopes, to already stressed geological structures when you also add 30-foot seas, extreme rainfall, and the lowest atmospheric pressure that the Western Pacific climate system currently knows how to produce? That is a different question. And the answer, as best we can determine it right now, is we do not fully know. And that uncertainty, hanging over 170,000 people with nowhere to go, is the thing that should be keeping emergency planners awake right now, and it should be keeping you watching. Part 3. The core claim. Let me state this plainly, because it deserves plainness. What is happening over the Mariana Islands right now is not just a typhoon story with a geology footnote. This is a compound hazard scenario, a situation in which two separate natural systems, each capable of generating significant damage independently, are overlapping in time and space in a way that current models are not designed to handle. That is the core claim of everything that follows in this video. Not that this earthquake caused the typhoon, not that the typhoon will trigger a mega-earthquake, not that civilization is crumbling. The claim is more specific and frankly more troubling than any of those dramatic framings. Our systems for understanding and responding to natural disasters are built around single-hazard thinking, and right now, over US territory, two hazards are active simultaneously. When we design a hurricane response, we optimize for hurricane variables, evacuation routes, storm surge modeling, wind-resistant construction codes. The entire framework is built on the assumption that the primary threat is atmospheric. When we design earthquake preparedness, we optimize for seismic variables, building codes that account for ground motion, tsunami warning systems, structural resilience requirements. That framework assumes the primary threat comes from the ground. There is no established framework for the conversation between the two. What happens when soil that is already saturated from typhoon rainfall experiences seismic loading? What happens when coastal infrastructure that has been undermined by surge and wave action then absorbs ground shaking? What happens when emergency responders who are sheltering from a Category 5 storm cannot simultaneously respond to a geological event? These are not hypothetical questions generated for dramatic effect. These are real engineering and emergency management questions that researchers in compound hazard analysis have been raising for roughly a decade, and the honest answer to all of them is, we have very little real-world data because these events rarely overlap this precisely. The reason they rarely overlap has to do with probability. A major typhoon over a specific piece of real estate is already a relatively rare event. A significant earthquake in the same window, even in a seismically active zone, adds another layer of rarity. The joint probability of both happening simultaneously is low enough that it has not historically driven emergency planning priorities. The problem is that low probability is not the same as impossible, and right now, in the present tense, both events are occurring over the same chain of islands. The low probability scenario has materialized. There is a concept in risk analysis called nonlinear amplification. The idea is that when you stack two stresses, the outcome is not simply the sum of the two individual outcomes. It can be something larger. A structure that might survive a Category 4 typhoon and would normally survive a moderate earthquake might not survive both in the same week, because typhoon damage changes the structure's remaining ability to absorb seismic loading. A slope that might hold under normal rainfall and would normally absorb a low-magnitude tremor might not hold if the rainfall has already saturated the material to the edge of its friction threshold. You are not adding risks. Under certain conditions, you are multiplying them. 170,000 people, no evacuation route, the strongest storm on Earth, a seismically active subduction zone registering events in the same window. And a planning framework that was never designed to answer the question those four facts are now collectively asking. That is where we are. I want to walk you through each layer carefully, because it deserves that. We're going to look at the storm in detail, how it got this strong this fast and what the ocean did to build it. Then we're going to go underground and talk about what the Mariana system actually looks like beneath those islands. And then we're going to put both layers on the same map and ask the question that does not appear to be getting asked tonight. But to do any of that effectively, you need to understand why this storm, arriving in April of 2026, is already an anomaly before you add a single seismic data point. Part 4. Why this has no modern precedent. April is not typhoon season. That sounds like a simple sentence, but it carries a lot of weight. The Western Pacific Typhoon Basin has a well-documented seasonal pattern. Activity builds through summer, peaks in August through October, and fades through late autumn. April sits in the climatological off-season, the period where the ocean has not yet accumulated enough heat for major storm development, and the atmospheric conditions that support tropical cyclone formation are typically unfavourable. The historical average for named storms in April in the Western Pacific is approximately 0.7 per year, less than one storm, a fraction of a storm, not zero, but close. And not only has Sinlaku formed in April, it has become a Category 5. A Category 5 in April in the Western Pacific represents a genuine statistical outlier. The record is not deep on April Category 5s in this basin. They are rare enough that when one occurs, it is not just a weather event. It is a signal worth examining. What does the intensification timeline look like? Over roughly 96 hours, Sinlaku moved through a sequence that should take longer under ordinary conditions: tropical depression, tropical storm, typhoon, super typhoon, Category 5. The rate of change crosses what meteorologists call rapid intensification thresholds, defined as a wind speed increase of at least 30 knots in a 24-hour period, and it appears Sinlaku crossed that threshold not once, but multiple times. That is not a storm that slowly built strength. That is a storm that accelerated in ways that compressed the available warning time. Here is why that compression matters for 170,000 people who cannot evacuate. On the mainland, when a storm rapidly intensifies from Category 3 to Category 5, the response is to move faster, accelerate evacuations, prepend mandatory orders, push resources forward. The infrastructure of escape, highways, airports, fuel depots, is still available even if the window shrinks. In the Marianas, there is no infrastructure of escape. The window closing faster does not change the available options. It changes only the amount of time people have to prepare in place, and when that window compresses, the consequences of under-preparation compound. Compare this for a moment to two storms that people in the Marianas know by name. Typhoon Pongsona struck Guam in December of 2002 with sustained winds of 150 miles per hour. The damage was catastrophic, and recovery took years. Typhoon Mawa struck Guam in May of 2023, still fresh in institutional memory, and caused an estimated $3.3 billion in damage. Mawa was a powerful storm. It also made landfall while weakening from its peak intensity. Sinlaku is approaching at or near its peak, and it is doing so in April, which means the seasonal preparation cycles are different, public alertness is different, and the institutional muscle memory of typhoon season is still, in some sense, dormant. Now here is the element that elevates this from remarkable weather event to something that genuinely has no clean modern precedent over US territory. Take the April anomaly, add the rapid intensification pattern, add the Category 5 ceiling, and then add the geological layer, a magnitude 5.0 earthquake on the same volcanic island arc at depth in the same time window. Each of those elements has occurred before in isolation. A deep Mariana earthquake happens regularly. An off-season Western Pacific typhoon happens occasionally. A Category 5 landfall happens somewhere in the basin every few years. But the specific combination, Category 5, April, CNMI and Guam in the direct path, no evacuation capacity, seismically active subduction zone registering events simultaneously, that combination does not have a clean historical analogue. We are not drawing on a library of previous events to forecast outcomes. We are in comparatively uncharted territory. Individually, what is happening tonight is explainable. Unusual but explainable. The ocean was warm enough. The atmosphere cooperated. The subduction zone did what subduction zones do. Each component has a perfectly reasonable scientific origin story. Together, they are unprecedented. And to understand why that word is not just dramatic here but operationally real, you need to understand the machinery. You need to understand how the storm became what it is. And that story begins not at the surface of the ocean, but underneath it. Part 5. The 96-hour transformation. Picture a loose cluster of thunderstorms spiralling over warm water, unremarkable. The kind of system that forecasters flag and watch but do not necessarily worry about. 4 days ago, that is roughly what Sinlaku was. A system with potential, sitting in a part of the Pacific where the water was warm and the atmospheric setup was cooperative. And then the transformation began. Day 1, it organizes. The low-pressure center tightens. The towering thunderstorms that are the engine of tropical cyclones start wrapping more symmetrically around that center. Day 2, it crosses the threshold into tropical storm classification. Sustained winds have reached 39 miles per hour, and the circulation is clearly defined. It has a name. Day 3 is where it gets remarkable. The structure shifts in what forecasters call rapid intensification. The eye, that haunting circular void at the center, begins to contract. As the eye contracts, the rotation around it accelerates, exactly the way a figure skater pulling in their arms spins faster. The surrounding eye wall tightens. The central pressure drops, and it drops quickly. 30 knots of wind speed added in 24 hours, then another 30. The rapid intensification threshold crossed once, then crossed again. By day 4, you have a Category 5, sustained winds near or above 157 miles per hour, an eye clearly visible on satellite, a storm that, if you watched its radar loop, would look almost geometric in its terrible symmetry. Now, here is why this pace matters for people who cannot leave. Warning systems and public communication are calibrated to the historical rhythm of storm intensification. When a storm follows a more gradual path from tropical storm to major typhoon, authorities have time to escalate messaging in digestible steps. The public has time to mentally process the rising threat and act accordingly. When a storm keeps outrunning its own forecast models, that calibration breaks down. The public may still be operating on yesterday's advisory, even as today's reality has changed dramatically. This is not a theoretical gap. Research on previous rapid intensification events found that this pattern consistently outpaces social preparedness, even when the technical forecasting is accurate. The storm is right, the public is behind. And Sinlaku, by any measure, intensified faster than events the Marianas have experienced in recent memory. There is a reason this storm reached Category 5 in April. The fuel source is not random, it is sitting right there in the ocean, and it connects this storm directly back to the same islands, the same geology, the same moment in time we started with. The water that powered Sinlaku floats above the deepest trench on the planet. That is not coincidence, that is geography. And geography, tonight, is fate. Part 6. Ocean heat, the real engine. The surface temperature of the ocean is what most people think of when they think about tropical cyclone fuel. Warm water evaporates, moisture rises, the atmospheric engine runs. That is correct as far as it goes, but it is incomplete in a way that turns out to matter enormously for understanding why Sinlaku reached Category 5 in April. The fuller story is ocean heat content, not just how warm the surface is, but how warm the water is from the surface down to a depth of roughly 26 meters, sometimes more. When a tropical cyclone passes over ocean, the churning stirs up that water column. If the warm layer is shallow, this stirring brings cooler water to the surface, which effectively starves the storm. That is one of the primary self-limiting mechanisms of tropical cyclones. The storm weakens its own fuel supply as it moves. But when the warm layer is thick, when the heat extends well below the surface, that self-limiting mechanism is suppressed. The storm churns, the warm water at depth replenishes the surface, and the fuel supply remains essentially uninterrupted. The storm can continue intensifying because the ocean refuses to cool down. The Western Pacific Warm Pool is one of the most thermally energetic bodies of water on the surface of the Earth. It sits in the region broadly bounded by the Philippines, Indonesia, and the Micronesian Islands, which is to say, the same water that Sinlaku has been moving through on its track toward the Marianas. Research published in 2019 documented a statistically significant increase in the proportion of tropical cyclones undergoing rapid intensification, and the mechanism identified points directly at this ocean heat content increase. The warm layer is getting thicker. The self-limiting mechanism is getting weaker. Storms that would historically have plateaued at Category 3 are now finding pathways to Category 5 that did not reliably exist a generation ago. The El Niño to neutral transition that the Pacific is currently moving through means that subsurface heat which accumulated during the El Niño phase is still present in the water column. A Kelvin wave, a pulse of warm water that travels beneath the surface from west to east across the Pacific, has been propagating through this region. Surface temperatures are warm, subsurface temperatures are warm. The thermal structure of the water column underneath Sinlaku gave the storm essentially no reason to weaken, and every reason to accelerate. And this is the direct link back to the situation over the Marianas tonight. The ocean that handed Sinlaku its Category 5 status sits above the Mariana Trench. The heat that allowed this storm to grow into the strongest system on Earth before making landfall on US territory floats above the same subduction zone that moved tonight. I am not suggesting those two facts are causally connected. They are not, in any direct physical sense, but they are geographically inseparable, and that geography means both the atmospheric extreme and the geological activity are centered on exactly the same piece of the planet. That piece of the planet has 170,000 people on it. The question the ocean heat data leaves us with is this: if the warm layer is thick enough to prevent the storm from weakening during its approach, If Sinlaku arrives at peak intensity rather than a spent post-peak state, what does that mean for ground that is already under seismic stress? The margin that might have existed between damaging and catastrophic has been erased by the same warm water that drives global weather. The implications of that are worth sitting with. Part 7. Why this storm did not stall. There is another variable in storm behaviour that is easy to overlook and that matters significantly for the Marianas scenario. Sinlaku has maintained its forward motion. It has not stalled, has not wobbled, has not meandered over open water the way some Western Pacific typhoons do. This is relevant because a stalling storm does something interesting. It begins to exhaust its own fuel supply, churning the same water repeatedly until that patch of ocean has given up most of its heat. Stalling is one of the mechanisms by which powerful storms weaken before landfall. The atmospheric steering pattern guiding Sinlaku has been consistent, a subtropical ridge to the north, funneling the storm along a northwest track with sustained forward velocity. No significant wind shear events, no blocking patterns forcing a loop or slowdown. The storm moved efficiently and maintained the structure that allowed continued intensification. In the language of tropical meteorology, it is a well-organised system operating in a favourable environment, which is a very polite way of saying the atmosphere gave it everything it needed and got out of the way. What this means practically is that the islands are not getting a storm that has had time to partially exhaust itself. They are getting the full, uninterrupted output of a system that the ocean fed continuously and that the atmosphere steered directly toward them. The energy that the Western Pacific has been building in that water column is going to arrive concentrated and intact over inhabited US territory, which brings us back to the ground. Because ground that is about to receive concentrated intact Category 5 energy, the rainfall, the surge, the wind loading, is not the same ground that received a quiet week of light rain. And whether or not tonight's seismic activity is a direct complicating factor, the physical state of the soil and slopes on those islands after Sinlaku passes is going to be fundamentally changed. That matters, and it matters more than usual here. To understand why, we need to go underground. Part 8. The April Anomaly. Let me put a number on the rarity of this timing. In an average April, the Western Pacific produces roughly 0.7 named tropical storms. That figure includes all intensity levels, not just typhoons, not just Category 5. Everything. The statistical expectation for April in this basin is less than one storm of any kind. April is quiet because sea surface temperatures in the Western Pacific, while warm year-round by global standards, sit several degrees below their summer peak. The intertropical convergence zone, which provides the low-level atmospheric convergence that tropical cyclones need to organise, is in its spring position, not yet shifted far enough north to support sustained activity over the Marianas. Upper-level outflow patterns that allow a storm to efficiently ventilate its heat are not yet optimised for typhoon development in this part of the basin. And yet, Category 5, April, direct track toward Guam and the CNMI. Whether this represents a genuine shift in the climatological baseline, or a low-probability event that simply happened to occur, is a genuinely open scientific question. Researchers are careful about attributing individual events to long-term trends, and that caution is appropriate. A single April Category 5 does not prove that April Category 5s are becoming common, but it does demonstrate that the conditions required to produce one are present, which means the historical assumption that such events are restricted to peak season is no longer as solid as it once was. And here is where the timing thread we have been following matters. The fact that this storm is occurring in April rather than August is not just a meteorological footnote. April is precisely the timing that placed this storm's peak intensity over the same island chain where seismic activity registered tonight. August and September have their own seismic background, but the specific alignment, this storm, this trajectory, this week, this geological moment is what brought both systems to bear simultaneously. Timing, it turns out, is everything, and to truly understand why, we need to go somewhere most storm coverage never goes, 226 kilometers straight down. Part 9. The World Beneath the Marianas. Before we can talk about what tonight's earthquake means, we need to talk about the flaw that produced it. And to do that properly, we need to visit the most extreme geological environment on this planet, sitting directly beneath the islands we have been discussing this entire time. The Mariana Trench is the single deepest structure on the surface of the Earth. Challenger. Deep, the lowest known point in the trench, descends approximately 10,935 metres below sea level. Put that in terms your brain can actually process. If you placed Mount Everest, the tallest mountain on land, at the bottom of the Mariana Trench, its summit would still sit more than a mile underwater. This is not just the deepest point in the ocean, it is the deepest point anywhere on the planet that we have been able to reach and measure. The trench exists because of subduction. The Pacific Plate, one of the largest tectonic plates on Earth, carrying some of the oldest oceanic crust in the world, rock that has been moving and aging for approximately 150 to 170 million years, is converging with the Philippine Sea Plate. The Pacific Plate is older, denser, and colder than the surrounding material. When two oceanic plates converge and one is denser, the denser one loses. It bends downward and begins its descent into the mantle. That process is subduction. The trench is the surface scar of where the bend happens, where the Pacific Plate tips over the edge and begins its long journey into the interior of the Earth. The convergence rate between these two plates is approximately 4 to 7 centimetres per year. That sounds slow, and in human terms it is, but sustained over millions of years it produces the Mariana system as we see it today. The deepest trench on Earth, the most extreme subduction angle, and a chain of volcanic islands that represent the above-water expression of what is happening kilometres below. Those volcanic islands are the Marianas: Guam, Rota, Tinian, Saipan, Pagan, Agrihan. The entire chain is not sitting on stable, passive oceanic crust. It is sitting on an island arc, a chain of volcanoes formed where the descending Pacific Plate reaches depths, where it releases water into the overlying mantle material, lowering the melting point and generating magma that rises toward the surface. The islands are literally built from the subduction process. They are the above-water tips of a volcanic chain whose roots connect directly to the grinding interface between two of the largest tectonic plates on the planet. What this means, and this is the crucial geographic reality for tonight's compound scenario, is that the islands do not merely sit near the seismic system, they are part of it. The volcanic arc is structurally connected to the trench. Seismic events in the arc, at the trench, or within the descending slab are all occurring within the same geological body that the islands sit upon. When we talk about a magnitude 5.0 earthquake near Pagan Island, we are talking about an event that occurred within the same geological structure that includes the rock and soil under every house, hospital, and emergency shelter on Guam and Saipan. Distance matters, depth matters, but geological connectivity is real and continuous. Now here is the layer that most seismic reporting skips, because it requires thinking about what old, cold oceanic crust actually does when it bends and descends. The Pacific Plate material subducting under the Marianas is some of the oldest oceanic crust on the planet. Old oceanic crust is cold oceanic crust. Cold rock is brittle rock. And brittle rock, subjected to the extraordinary pressures of subduction, does not simply bend and flow the way warmer, younger material would. It breaks, it fractures. The descending slab carries its brittleness with it as it sinks, which is part of why the Mariana system produces earthquakes at depths that most other subduction zones do not. The slab retains its mechanical integrity well below the depths where other plates would have deformed plastically. 226 kilometers of depth is within what seismologists call the Wadati-Benioff zone, the plane of earthquake activity that traces the descending slab as it subducts. This is exactly where tonight's earthquake was generated. Inside the cold, brittle slab of Pacific crust, in the zone where accumulated stress produces ruptures that occasionally reach the surface above. The islands are above, the slab is below, the trench is between them, and right now a Category 5 typhoon is bearing down from the surface, while the slab beneath registers activity in the dark. To understand what that activity might mean, and what it might not mean, we need to understand what a 226-kilometre earthquake is actually telling us. And the answer is more nuanced, and in certain scenarios more concerning, than a simple magnitude number would suggest. Part 10. The meaning of a 226-kilometre earthquake. Here is a thing about deep earthquakes that most reporting gets wrong by implication. When a shallow earthquake occurs, say, at 10 or 15 kilometres of depth, The energy release is close to the surface. The ground shaking is intense, and if the rupture occurs underwater, tsunami generation is a real and immediate concern. Shallow earthquakes near coastlines are the ones that kill people directly and trigger warning sirens. When journalists and emergency managers think about earthquake risk, they are mostly thinking about shallow earthquakes. Deep earthquakes are different. An event at 226 kilometers is occurring roughly 140 miles underground. The seismic waves that reach the surface have traveled through enormous amounts of material, and that material attenuates, absorbs and disperses the energy along the way. So the shaking at the surface for a given magnitude is less intense than it would be for a shallow event. A magnitude 5 at 226 kilometers produces far less violent surface motion than a magnitude 5 at 10 kilometers. This is why deep slab earthquakes, even in populated regions, are often barely felt at the surface, despite being clearly detectable on seismographs. The instruments notice, your body probably not. The other key characteristic, no tsunami. Tsunami generation requires rapid, large-scale vertical displacement of the seafloor. Deep earthquakes, by definition, occur far below the seafloor. The displacement happens in rock, not water, at a depth where the energy cannot efficiently translate into the kind of seafloor movement that drives a destructive wave. 226 kilometers is well below the range where meaningful seafloor displacement is generated. This is not a debate among seismologists, it is settled physics. No tsunami was generated tonight, and that is correct. So in one sense, tonight's earthquake is properly classified as a non-event, and yet, the deeper story is about what a deep slab earthquake tells us about the state of the system producing it. The Wadati-Benioff zone is not a random scattering of stress, it is a structured plane of seismicity that traces the descending slab. Earthquakes within it occur because the slab is under stress. The forces of subduction load it from one direction, while the resistance of surrounding mantle material pushes back from another. The brittleness of the old Pacific crust means stress accumulates in the slab, rather than being released gradually through slow deformation. When that accumulated stress reaches the breaking point for a given portion of the slab, you get an earthquake. The magnitude corresponds to how much stress was released in that event. Tonight's magnitude 5 is a relatively modest release on the scale of what this system is capable of. The magnitude scale is logarithmic, meaning each unit represents approximately 32 times more energy than the one below it. A magnitude 5 and a magnitude 6 are not close. They are 32 times apart in energy release. But here is the question that compound hazard researchers find worth asking. Does a seismic event in the Wadati-Benioff zone, even a modest one, tell us anything about the stress state of shallower portions of the same system? Can energy redistribution at depth influence the likelihood of activity closer to the surface? This is not settled science. There is active research on what seismologists call stress transfer, the idea that a rupture in one part of a fault system can change the stress balance in adjacent portions, either promoting or suppressing future events. The geometry of the Mariana Arc, the connectivity between the slab and the shallower megathrust interface, the relationship between arc seismicity and the overlying volcanic system, these remain subjects of ongoing study. I am not telling you tonight's earthquake is a precursor. I am not telling you the system is about to produce a shallower, larger event. I genuinely do not know, and anyone telling you they do know is operating beyond what the current data supports. What I am telling you is that the question of whether the Mariana geological system is in an elevated state and what that means for surface conditions about to receive a Category 5 typhoon is a question worth taking seriously. Because the ground above that 226-kilometer earthquake is about to be loaded from above in the most extreme way the atmosphere knows how to load it. 30 feet of seas against coastlines, rainfall measured in inches per hour across volcanic island slopes, wind loading on structures that were not all built to current standards. The typhoon alone changes the physical state of those islands. The geological activity beneath them, even at depth, even at modest magnitude, is a variable that belongs in the same conversation. And that conversation has to include one specific island that is more than just a dot on the earthquake report. Part 11. Pagan Island, not just a dot. 300 kilometers north of Saipan, Pagan Island rises from the Pacific as two connected volcanic edifices, Mount Pagan to the north and South Pagan to the south. separated by a low isthmus. Together they form what geologists classify as a stratovolcano complex, steep-sided, built from alternating layers of lava, ash, and pyroclastic material. The kind of volcanic structure that produces dramatic topography and, under certain conditions, dramatic instability. Pagan has a human history as well as a geological one. It was inhabited for centuries, and its most recent modern community was evacuated in 1981 following a major eruption, one that buried the island in ash and made habitation impractical for years. The most recent significant eruptive activity was in 2012, rated Volcanic Explosivity Index 2, a relatively minor eruption by global standards, but a reminder that the volcanic system beneath Pagan is not dormant. It is quiet. There is a difference. That distinction, active versus dormant, matters for how we think about slope stability. Volcanic islands built from repeated eruptions have a specific material composition that makes them behave differently under stress than islands built from older, more consolidated rock. The slopes of stratovolcanoes like Pagan are composed of layers that include loose pyroclastic material, hydrothermally altered rock that has been chemically weakened by interaction with volcanic fluids, and unconsolidated ash deposits. These layers do not have the same cohesive strength as solid basalt or granite. They are susceptible to what geologists call flank instability, the tendency for portions of a volcanic slope to fail, particularly when subjected to external loading like heavy rainfall or ground shaking. The underwater flanks of these volcanic islands, the portions of the edifice extending below sea level, are often steeper and composed of the same vulnerable material. Submarine landslides on volcanic island flanks are not theoretical events. They have occurred on volcanic islands around the world. The Canary Islands have a well-documented history of large-scale flank collapses. Hawaii's geological record includes the signatures of enormous prehistoric submarine landslides, some of which generated waves that were detected across the Pacific. The geological record of the Pacific Island Arc system contains evidence of similar events at multiple sites. The mechanism for triggering these events includes both seismic loading and rapid saturation of volcanic material. Ground shaking reduces the shear strength of slope materials, particularly those that are already wet. Rapid rainfall, the kind a Category 5 typhoon produces, saturates slopes and raises the groundwater table, further reducing the effective friction that holds those materials in place. When both processes occur in the same time window, the stability threshold for a given slope is reached at a lower level of combined stress than either process alone would require. Here I want to be careful about scale. Tonight's magnitude 5.0 at 226 kilometers is below the threshold that seismologists typically associate with spontaneous triggering of major submarine landslides. The commonly cited threshold for earthquake-triggered submarine collapses is in the magnitude 6.5 to 7 range, with shallower events being more effective triggers than deeper ones. Tonight's event is smaller and deeper than that typical trigger profile. We're not in a situation where a major slope collapse is an immediate and likely outcome of tonight's seismicity. But we are in a situation where a volcanic island with inherently unstable slope material is going to receive Category 5 typhoon conditions in the same general time window as a seismic event in its immediate vicinity. And the question of how those two processes interact, even if neither alone would trigger failure, is not one that existing emergency management frameworks are designed to address systematically. The word scenario is doing a lot of work in this part of the video, and I want to own that. I am building a scenario, a theoretical chain of events, each grounded in documented geological processes that could unfold when the conditions we have been discussing converge. I am not predicting it will occur. I am arguing it belongs in the conversation, precisely because it does not currently appear to be there. When forecasters focus on the typhoon and seismologists note the earthquake, and neither talks to the other, the space between them, the compound interaction zone, goes unexamined. That space is exactly where the most uncomfortable question lives. Part 12. The uncomfortable question. Here is the question, and I want to be honest about exactly what the data supports and what it does not. Tonight's magnitude 5 earthquake at depth does not tell us, by itself, that the Mariana seismic system is in an elevated state. It is consistent with the normal background seismicity of a highly active subduction zone. On any given week in the Mariana Arc, you might see several events at this magnitude. So in one honest reading, the answer to does this earthquake tell us something alarming is not definitively, no. But here is the concept I want to introduce carefully: clustered seismicity. In seismically active regions, earthquakes do not always occur in perfect isolation from each other. There are periods of elevated activity, windows in which a zone produces more events than its baseline rate would predict, and there are periods of relative quiet. Identifying a cluster versus a background fluctuation in real time is genuinely difficult. The difference often only becomes clear in retrospect, after a longer sequence has developed. This is one of the fundamental frustrations of operational seismology. The signals that matter most are often the hardest to read in the moment they're happening. The Mariana system is registering activity right now. Whether tonight's event is part of an elevated cluster or simply a point on a normal background distribution is something that scientists monitoring the zone are better positioned to assess than I am. What I can say is that the timing, an event occurring in the hours around the Category 5 upgrade of a storm heading directly for the Arc, creates a compound context that does not exist when any single event in this zone is reported in isolation. Now let me connect this to the physical question that the typhoon raises. The storm is going to deposit extraordinary amounts of water on those islands, not unusual amounts for a typhoon, Category 5 amounts. Rainfall rates that can reach several inches per hour. Total storm accumulations measured in feet. That water is going to saturate the soil. It is going to raise groundwater tables. It is going to change the effective weight pressing on slopes. It is going to flow into subsurface cracks and pore spaces that, in their normal state, provide friction and cohesion to geological structures. Geotechnical engineers call this pore pressure increase. When water saturates soil and rock, the water pressure in the pore spaces pushes outward against the friction holding the material together. High enough pore pressure and friction drops. Slope materials that were stable in dry conditions become unstable. This is the mechanism behind most rainfall-triggered landslides, one of the most consistent secondary hazards associated with major tropical cyclones worldwide. Now introduce the seismic dimension. Even at modest magnitude and significant depth, a seismic event produces ground motion that can affect the structure of slope materials, particularly those already close to their stability threshold. In geotechnical terms, seismic shaking can induce liquefaction in saturated granular materials, reducing their effective strength dramatically. It can also act as a trigger for slopes that rainfall saturation has brought to the edge of failure. The final increment of stress that pushes them over. The scenario I am describing does not require a major shallow earthquake. It does not require a landslide of catastrophic scale. It requires only that the seismic background activity of the Mariana system remains non-zero, which it reliably does, during the window when the typhoon is depositing maximum water on slopes that are geologically susceptible. That window is open right now, the typhoon is coming, the seismic system is active, the ground is about to be loaded from above in the most extreme way the climate system knows how to load it. And when I say the system is active and being loaded from above, I do not mean that metaphorically, I mean it in the most specific physical sense possible. 170,000 people are living on the surface of that loaded system. The planning frameworks designed to protect them were not designed for this combination. The collision between those two systems is what we need to examine next, and what that collision looks like in practice, in soil, in concrete, in emergency response capacity, is the centre of what this story is actually about. Part 13. The overlap problem. Let us start with a definition, because precision matters here. A compound hazard, in the technical language of disaster risk research, is a situation in which two or more hazardous events occur simultaneously, or in close succession, and interact in a way that amplifies the overall risk beyond what either event would produce independently. The key word is interact. It is not simply that two bad things happen at the same time. It is that their interaction, through shared physical processes, shared infrastructure, or shared response resources, produces outcomes that the sum of two independent events would not predict. Single hazard frameworks are the dominant model in emergency management. A hurricane emergency operations plan is designed to optimize the response to a hurricane. A seismic preparedness plan is designed to optimize the response to an earthquake. Personnel, resource flows, decision trees, communication protocols, all structured around one primary event with defined characteristics. When the primary event is a Category 5 typhoon, the framework activates typhoon response. When it is an earthquake, the framework activates seismic response. There is no established compound response framework for Category 5 typhoon plus active subduction zone seismicity, because this combination has not historically been frequent enough to drive the development of one. That is not a criticism of emergency management professionals. They are working with the planning tools that exist, built on the historical record of events that have actually occurred and been studied. The historical record simply has very little data on this specific combination over the specific geography of the Marianas. What does that gap look like in practice? Consider what I would call the synchronization problem. When a typhoon is active, emergency responders are pre-positioned in shelters and hardened facilities. They are not moving, because moving in a Category 5 typhoon is how responders become victims. Response capability is essentially frozen during the height of the storm. If, during that frozen window, a seismic event of sufficient magnitude and proximity were to occur, generating ground failures, slope collapses, or infrastructure damage, the response to that secondary event would have to wait until the primary event permitted operations to resume. The two events would not receive simultaneous response. They would receive sequential response. And the sequence matters enormously when lives depend on timing. System fragility is the other concept worth naming here. Engineered systems, buildings, bridges, power networks, water treatment facilities are designed with a certain safety margin. That margin accounts for the expected range of loading the system will experience over its life. A building designed to Category 4 wind loading might have a margin that extends to weak Category 5 conditions. That same building might also have a seismic design that accommodates a moderate earthquake at typical regional depth. But those margins are evaluated independently. The question of whether a building that has absorbed Category 5 wind damage still retains its designed seismic resistance capacity has not been systematically addressed in most building codes, because the joint probability of experiencing both in the same event has historically been too low to drive code development. For Guam and the CNMI, where building codes have not always been enforced with mainland consistency, where some building stock predates modern standards, and where Typhoon Mawa in 2023 revealed existing vulnerabilities across the infrastructure, the effective safety margin for a compound event is even thinner than code values would suggest. And the island isolation factor layers onto all of this. Supply chains to the Marianas under normal conditions are measured in days. During a major typhoon and its aftermath, they extend to weeks. The port infrastructure that brings in building materials, emergency supplies, fuel and food is the same infrastructure at risk from typhoon surge and wave action. In a compound event where additional geological damage has also occurred, the logistical challenge becomes substantially more complex. 170,000 people. Planning frameworks built for one event at a time, infrastructure margins evaluated independently for wind and for ground motion, a supply chain measured in weeks even under the best conditions, and now two systems, the strongest storm on Earth and an active subduction zone, operating simultaneously on the same geography. Part 14. Saturation and instability. Rain is not just weather. In a geological context, rain is a loading event, a force applied to the surface of the Earth that changes the mechanical properties of everything it contacts. And a Category 5 typhoon does not deliver rainfall in gentle, absorbable increments. It delivers it as a sustained assault, for hours, at rates that exceed the capacity of the ground to drain, the rivers to carry, and the engineered drainage systems to handle. The first stage is familiar: flooding. Surface runoff from intense rainfall collects in low areas, blocks roads, enters buildings. Emergency managers plan for this, and their plans are calibrated to the depth and duration of historical flooding events. The second stage is less visible and more consequential for a compound scenario. As rainfall continues, water that does not run off infiltrates into the soil's pore spaces fill, the groundwater table rises. In volcanic island terrain, which describes the Marianas, the soil overlying the volcanic rock is often composed of materials with relatively low permeability in their clay-rich horizons and higher permeability in fractured volcanic zones. Water moves through these systems unevenly, creating localized zones of saturation that can develop faster than surface monitoring would indicate. When a slope reaches full saturation, its behaviour changes fundamentally. In dry soil, the friction between particles and the cohesion of clay minerals hold the slope together. As water fills the pore spaces, it exerts pressure that pushes particles apart and reduces effective friction. Dry sand holds a slope at a certain angle, wet sand at the same angle flows. The same principle applies to the volcanic soil and weathered rock on typhoon-soaked island terrain, just at a scale that can involve entire hillsides. Slope failures, landslides, are the direct consequence of this process. The Marianas have experienced landslides during previous major typhoons, and they will experience them during Sinlaku. The question is not whether landslides will occur. They will. The question is where, how large, and whether their consequences are amplified by any concurrent seismic activity. Here is where the geological layer re-enters. Slopes brought close to their stability threshold by rainfall saturation. Slopes where only a small additional increment of stress is needed to initiate failure become susceptible to seismic triggering. A ground motion that would be inconsequential on a dry, stable slope can provide the final push on a saturated, near-critical one. The seismic event does not need to be large. It needs to arrive at the right moment. That moment is during or shortly after peak rainfall, which is also, by definition, during or shortly after the passage of a Category 5 typhoon. Coastal erosion is the other process worth naming. 30-foot seas driven by a Category 5 typhoon exert enormous force on coastlines. The bases of coastal cliffs, the faces of seawalls, the foundations of structures near shorelines all receive impacts that undermine structural integrity. When surge carries sediment away from the base of a cliff, it removes the support that was holding the upper portion in place. Coastal failures driven by undercutting at the base are documented consequences of major typhoon events, and they are distinct from rainfall-triggered inland landslides, though both are happening in the same storm. The submarine coastal slopes are at risk as well. The seafloor drops steeply away from the volcanic Marianas. These are not gently sloping continental shelf environments. Material destabilized, and sliding off an island's submarine flank does not drift gently to the bottom. It moves fast, and moving underwater material displaces water. I want to be precise about what I am building toward. I'm not claiming that a major tsunami-generating event is a likely outcome of tonight's situation. I am building toward a scenario, a theoretical chain of events grounded in documented geological processes. Because in the full range of possible outcomes for the next 48 hours, there is a possibility that is not currently appearing on the same page as the typhoon forecast, and it deserves to be named. Part 15. The Submarine Landslide Scenario. Let me describe a sequence, not prediction. A sequence of physical events, each grounded in documented geological process, that could unfold when the conditions we have been discussing converge in the same place at the same time. A volcanic island composed of alternating layers of lava, pyroclastic deposits, and hydrothermally altered rock has been accumulating material on steep submarine flanks for thousands of years. Those flanks extend from the shoreline down to great depths, at angles that in some cases approach or exceed the angle of repose, the steepest angle at which a given material remains stable. The only reason these slopes maintain their structure is the mechanical strength of competent volcanic rock layers acting as scaffolding, holding the weaker material in place. A major typhoon arrives. Rainfall saturates the exposed land surface and infiltrates the volcanic edifice. Groundwater tables rise within the volcanic rock, increasing pore pressure throughout the structure, including within the submarine flanks below the waterline, where hydrogeological connectivity allows storm-driven pressure increases to propagate offshore. Simultaneously, 30-foot seas pound the base of the island's coastal cliffs, removing material that was providing lateral support, and the seismic system registers activity. Even at depth and modest magnitude, seismic waves add dynamic stress to slopes already close to their stability threshold. The frequency content of the waves, lower frequencies travel more efficiently through rock and saturated soil, may be sufficient to push a near-critical slope over the edge. Somewhere on a submarine flank, potentially any of the volcanic islands in the chain, a slope that has been loaded by all three processes simultaneously reaches the point where friction can no longer hold. A section mobilizes. It moves downslope. The mass of that material displaces water as it goes. Water displaced by a submarine mass movement does not simply absorb the energy, it transmits it. The displacement generates a wave, not the wave generated by a fault moving the seafloor. but a wave generated by solid material scooping water out of the way. This is the mechanism behind what researchers call displacement waves, and they are distinct from seismically generated tsunamis in important ways. Traditional seismic tsunamis are generated by the vertical displacement of large seafloor areas along a megathrust fault. They are detected by the global dartbuoy network. They propagate over long distances. Warning systems are specifically designed for them. Displacement waves from submarine landslides are more localized, more variable in direction, and potentially faster to arrive at nearby shorelines because the source is close. In some documented historical cases, the wave arrived at a nearby shoreline before warning systems could activate. I want to be responsible about the threshold question. Triggering a submarine landslide large enough to generate a meaningful displacement wave typically requires either a very large seismic event, generally magnitude 6.5 or greater, shallower than tonight's, or a preconditioned slope already near critical instability. Tonight's magnitude, 5 at 226 kilometers, is below that typical trigger profile. The vast majority of submarine slopes in the Marianas are not critically unstable under normal conditions. What the compound scenario does is change the definition of normal. A slope requiring a magnitude 6.5 to mobilize under dry unloaded conditions may require something smaller if it is simultaneously saturated by a Category 5 typhoon and loaded by ground motion from even a moderate event. The threshold shifts downward. By how much? That depends on the specific material properties of each slope, the degree of pre-existing saturation, the depth of the water table, and a dozen other variables that we cannot assess in real time from the outside. This is the scenario. Not certain, not imminent. A threshold that is lower tonight than it was last week, over the same islands, above the same 170,000 people. And above all of this, above the soil and the slopes and the seismic uncertainty, sits infrastructure about to face the most severe test it has encountered in decades. Part 16. Infrastructure Stress Test. Guam's infrastructure is not a mystery. After Typhoon Mawar in 2023, there was substantial documentation of what a major typhoon does to the island's engineered systems. $3.3 billion in estimated damage. Power outages affecting nearly the entire island, some lasting months rather than weeks. Water system failures as treatment plants lost power and pressure. Road closures from landslides, flooding and structural collapse. A port that struggled to handle the surge in incoming recovery supplies, while simultaneously managing damage to its own facilities. A recovery timeline measured in months even with significant federal support. That is the baseline, a powerful but not Category 5 typhoon. Sinlaku is approaching as Category 5. The power grid is the critical single point of failure from which almost every downstream consequence flows. When it goes down, and it will go down, because no grid is engineered to survive Category 5 wind loading without significant damage, the consequences cascade immediately. Hospitals fall back on generator power. Generators carry fuel reserves measured in hours to days, not weeks. Water pumping stations stop. Wastewater treatment stops. Refrigerated medications and food supplies begin to warm. Air conditioning in a tropical climate is not a comfort issue. It is a medical issue for vulnerable populations who cannot thermoregulate without it. The moment the grid fails, a clock starts for every other critical system on those islands. Hospitals deserve particular attention. Guam's hospital capacity is limited relative to the population it serves. The Naval Hospital Guam has hardened facilities that give it better structural resilience than civilian counterparts, but the civilian population also relies on Guam Memorial Hospital and other facilities that face serious operational challenges after Mawar. In a compound event, where both typhoon injuries and any geological event injuries would be presenting simultaneously, capacity becomes acute. Emergency medical care is a resource that gets consumed quickly when demand spikes, and it cannot be resupplied from the mainland in hours. The aircraft that might bring additional medical resources cannot fly through a Category 5 typhoon. They are waiting on the ground somewhere thousands of miles away. Supply chain isolation is Guam's structural vulnerability in any major disaster scenario, and it does not receive enough attention in mainland coverage. The Marianas are not connected to the global supply chain the way mainland ports are. Container ships arrive on a schedule calibrated to normal demand. Fuel is held in limited on-island storage. Building materials for recovery, lumber, roofing, concrete must be ordered and shipped from thousands of miles away. After Mawa, some Guam residents waited months for construction materials to repair their homes, not because of bureaucratic failure, but because the physical logistics of supplying an island in the middle of the Western Pacific are genuinely difficult. Distance is not a policy problem. Distance is a physics problem. A Category 5 typhoon, followed by any additional geological event, even one well below catastrophic thresholds, would extend that recovery timeline. Every additional element of damage adds to the volume of materials needed. Every additional element of infrastructure failure adds to the list of systems requiring repair before the community can function normally. The compounding is not linear. It is not Mawa plus a little more. It is potentially Mawa multiplied by a factor whose value depends on variables that are, right now, unresolved. $3.3 billion from a powerful but not peak typhoon. Category 5 approaching. Active subduction zone. 170,000 people. No evacuation route. A recovery supply chain measured in weeks under the best conditions. Those numbers describe a stress test that the Marianas have not faced before, not in the modern era, not with this combination of atmospheric and geological simultaneity. And the systems being tested were not designed for this exam. There are layers beneath even this, more speculative, more contested, and in some ways more disturbing. Questions about whether the boundary between atmosphere and geology is quite as clean as emergency planners assume. Part 17. Can storms trigger earthquakes? Here is a question that makes most geologists uncomfortable. Can an atmospheric event, a tropical cyclone, actually influence seismic activity? The conventional answer, delivered with appropriate scientific caution, is almost certainly not in any meaningful way for events of this scale. Earthquakes are driven by the accumulation and release of tectonic stress over years to decades. A typhoon lasts days. The energy scales are vastly different. But that is not quite the end of the story. There is a hypothesis, studied in the scientific literature, not just on the internet, that relates to what happens to the crust when a large tropical cyclone passes over it. The atmospheric pressure at the centre of a major typhoon can drop to extraordinarily low values. Typhoon Tip in 1979 holds the record at 870 millibars, roughly 87% of standard sea level pressure. That drop in atmospheric load is, in a real physical sense, a reduction in the weight pressing down on the crust beneath the storm. The hypothesis is that fault systems already near their failure stress threshold might be very slightly influenced by this change in surface loading, an uncorking of accumulated stress. Researchers in Taiwan published work examining correlations between typhoon passage and slow earthquake events, periods of subtle, slow fault movement detected by sensitive GPS instruments. The correlations found were small, the mechanism proposed was tenuous, and the scientific community received it with appropriate caution. This is not established consensus. It is a finding that has been noted, examined, and not yet convincingly replicated in a way that would move it from interesting to operational. What the low-pressure uncorking hypothesis represents in the context of tonight's situation is not a confirmed mechanism. It is an example of how the boundary between atmospheric and geological systems may be less impermeable than we assume. If fault systems near failure threshold can be influenced, even very slightly, by the surface loading changes associated with a Category 5 typhoon passing directly over them, then the separation we maintain in our models between storm risk and earthquake risk may be overstated. I want to be precise. I am not claiming the typhoon triggered tonight's earthquake. The timing does not establish causation, and the physics are not convincingly established in the literature. What I am claiming is that the question of atmospheric geological coupling deserves more attention than it currently receives, and that attention is most urgently needed when, as is the case tonight, both systems are simultaneously peaked over the same inhabited geography. 170,000 people, 2 systems, 1 framework. The gap between what we know and what we are planning for is visible tonight in a way it is not always visible. Part 18. The military silence question. Guam is not simply a civilian population centre. It hosts Andersen Air Force Base and Naval Base Guam, 2 of the most strategically significant military installations in the Western Pacific. Andersen hosts bomber and surveillance assets. The naval base supports submarine and surface operations across the Indo-Pacific. In the context of current geopolitical competition in the region, These installations are not incidental, they are central. The military operates under its own Tropical Cyclone Condition of Readiness System, TCCOR, which stages preparation levels in advance of major storms. Military facilities have hardened infrastructure, pre-positioned resources, and response capabilities that exceed what is available to the civilian population. After Mawa, military assets were central to the early response and recovery on Guam. The question that deserves acknowledgement without overclaiming is this: how much of what happens to military readiness under a compound event, a Category 5 typhoon coinciding with geological instability, is transparent to the civilian population that shares the same islands? The military does not publicise its operational status. That is appropriate for operational security reasons, but it creates an information asymmetry at exactly the moment when the civilian population is most in need of confidence about the full picture of response capacity. This is not an accusation. It is an observation about the structure of information flow during compound events over territory that is simultaneously civilian and military. The question of whether hardened military infrastructure performs as designed when subjected to compound loading, wind, water, and seismic stress in sequence is one that the public cannot easily evaluate from the outside. What we can say is that even the best hardened infrastructure has limits, and the limits of that infrastructure during the event we are watching unfold are being tested in ways that no test scenario likely anticipated. Part 19. The Forgotten Americans narrative. Here is a fact that I think deserves to be stated plainly, in its full weight, without softening. The residents of Guam, Saipan, Tinian, and Rota are American citizens. They serve in the US military at rates that exceed those of most states, a remarkable level of service commitment from a population that, in return, has limited representation in the federal government. They cannot vote for president. They have a non-voting delegate in the House. They have no representation in the Senate. When federal decisions are made about disaster preparedness funding, infrastructure investment, or the speed and scale of post-disaster federal response, the political weight of 170,000 territorial residents is structurally lower than the political weight of the same number of people in a state. Typhoon Mawa in 2023 generated significant criticism of federal response speed and scale relative to what would have been deployed for an equivalent event on the mainland. $3.3 billion in damage. Months without power for large portions of the island. Recovery still incomplete in some areas more than a year later. The conversation about whether territorial Americans receive genuinely equal federal protection, not equal in law, but equal in practice, equal in political prioritization, equal in the speed of resources, was accelerated by Mawa and has not been resolved. Now Sinlaku arrives as Category 5, and the compound element, the geological layer that this video has been examining, makes the calculus even starker. The argument that territorial residents receive less than they would if they were in a state is not a fringe grievance. It is a documented pattern. And when compound hazard reduces the margin for error in emergency response, the consequences of that structural gap are not abstract. They are measured in recovery time, in lives disrupted, and in the slow erosion of resilience in communities that have already been told, in practice if not in policy, that they are second in line. 170,000 people. The strongest storm on Earth, a seismically active subduction zone, and a political structure that does not give them the representation needed to change any of this through the normal mechanisms of democratic pressure. That is the human layer of the compound hazard, and it belongs in the same conversation as the atmospheric and geological ones. Part 20. The Mega Event Fear. I need to address something directly, because if you have spent any time reading about the Mariana Trench and earthquakes online, you have almost certainly encountered it. Maybe it came up in a YouTube recommendation. Maybe it was a Reddit thread that kept you up later than you planned. Maybe it was one of those articles with a headline so alarming you clicked it, and then immediately wished you had not. The idea that the Mariana system is quietly building toward a megathrust event, an enormous, civilization-disrupting earthquake along the subduction zone, has significant presence in certain corners of internet geology speculation. And I want to talk about it honestly, because the way it usually gets discussed is either so catastrophist that it becomes useless, or so dismissively debunked that it leaves out things that are genuinely worth knowing. So let me try to do something different. Let me separate the fear from the science carefully, layer by layer, and show you where the line actually sits. First, the part that is real. The Mariana subduction zone is, in principle, capable of producing very large earthquakes. That is not speculation. That is basic plate tectonics. The mechanics of subduction, one plate diving beneath another, stress accumulating over decades and centuries at the locked interface between them, can generate megathrust events at subduction zones globally. The historical and paleoseismic record of the Pacific Rim includes evidence of events well above magnitude 8. The Cascadia subduction zone off the coast of the Pacific Northwest produced a magnitude 9 event in January of 1700. The Tohoku earthquake off Japan in 2011 reached magnitude 9.0 and generated the tsunami that caused the Fukushima nuclear disaster. The Valdivia earthquake in Chile in 1960, still the largest instrumentally recorded earthquake in history, was a magnitude 9.5. These are real events produced by real subduction systems, and the mechanism that produced them exists in some form in every subduction zone on the planet. So when someone tells you the Mariana system is a subduction zone, and subduction zones can produce enormous earthquakes, they are not wrong in any simple factual sense. The architecture is there. Here is where the internet version of this story usually goes off the rails. The question is not whether a subduction zone exists. The question is what kind of subduction zone it is, because not all subduction zones behave the same way, and the differences between them are not minor details. They are the entire ballgame when it comes to assessing the actual risk of a catastrophic megathrust event. The Mariana subduction zone has a specific geometry that makes it genuinely unusual among the major subduction systems of the Pacific. The Pacific plate subducting under the Philippine Sea Plate is old. Very old. We are talking about oceanic crust that has been moving and cooling for approximately 150 to 170 million years. Old oceanic crust is cold oceanic crust, and cold oceanic crust is dense. When that cold, dense slab reaches the subduction zone, it does not gently bend and slide. It plunges steeply, at an angle far more extreme than, say, the Cascadia system or the Chilean subduction zone. This steep geometry has a specific consequence for what seismologists call plate coupling. Plate coupling is the degree to which the two plates are mechanically locked together at their interface. High coupling means the plates are effectively stuck to each other, building up stress that releases catastrophically when the lock finally breaks. That is how you get a magnitude 9. Low coupling means the plates are sliding past each other more freely, accumulating less stress at the interface, and releasing it in smaller, more frequent events rather than one enormous rupture. What the scientific literature suggests, and I want to be precise here, because this is an active area of research and the community has not reached a definitive consensus, is that the specific geometry of the Mariana system, with its old, cold, steeply subducting slab, may produce relatively low coupling between the plates. The steep angle means the interface between the two plates is less extensive. The cold slab material may behave differently under pressure than warmer slab material at other subduction zones. Some researchers have argued that these factors combine to lower the maximum magnitude of potential megathrust events in the Mariana system, compared to the better-known catastrophic subduction zones elsewhere in the Pacific. I want to be very careful about what I am and am not saying here. This does not mean the Mariana system is safe. It does not mean a large earthquake is impossible. It does not mean you should dismiss seismic activity in the region as irrelevant. What it means is that the question of maximum possible event size is considerably more nuanced than either the catastrophist speculation or the breezy dismissive reassurance would suggest. The people online telling you a civilization-ending megathrust is imminent in the Marianas are outrunning the science. The people telling you there is nothing to think about here are also outrunning the science, just in the other direction. The honest answer, the one that the actual researchers in this field would give you if you asked them directly, is, we are still working on it. The coupling estimates for the Mariana system carry significant uncertainty. The paleoseismic record, the geological evidence of past large earthquakes preserved in sediments and coastal features, is limited compared to what we have for Cascadia or Japan. The instruments needed to precisely characterize the stress state of the plate interface are expensive, difficult to deploy in deep ocean environments, and not present in the density that would let us make confident statements. We know a lot about this system. We also have significant gaps. Now, tonight's magnitude 5.0. I want to address this directly because I can already imagine the comments, and some of them are going to connect these dots in ways I need to preemptively untangle. Tonight's deep slab event at 226 kilometers does not tell us anything about where the megathrust stress state stands. Let me explain why, because this is not a rhetorical dodge, it is a genuine physical distinction. The deep slab earthquake occurred within the subducting Pacific plate itself, inside the material that is descending into the mantle. The megathrust interface, the locked zone between the two plates where a catastrophic rupture would originate, is a different structure at a different geometry and a different depth range. These are not the same fault system, they are not the same stress regime. An event within the slab does not necessarily tell us anything about the state of the interface above it. The same way a stress fracture inside a steel beam does not tell you whether the bolts connecting it to the next beam are about to fail. Related system, different component, different failure mode. So tonight's earthquake is not a mega thrust warning. I want to be unambiguous about that. But here is what I also want to say, and I think it matters. The fear, the widespread, persistent, internet-amplified sense that something enormous is possible in this system is not irrational. It is not the product of stupidity or paranoia. It is a response to real geological complexity that has been imprecisely understood and inadequately communicated to the public. The Mariana system is genuinely extreme. The trench is the deepest point on Earth. The subduction is among the most dramatic on the planet. The volcanic arc sitting above it is active. The seismic background is elevated. These are real facts, and they produce real unease in people who are paying attention and trying to understand what they mean. The failure is not in the people feeling uneasy. The failure is in the gap between what the science actually says and what gets communicated publicly about this system. That gap is where the catastrophist speculation lives, and it lives there because legitimate scientific nuance rarely travels as fast as a terrifying headline. What matters for the next 48 hours has nothing to do with theoretical maximums or worst-case geological scenarios. What matters is the actual, present-tense, right-now interaction between the strongest storm on Earth and an active subduction zone, bearing down together on 170,000 people who are already running out of time to prepare. The megathrust question is real, and it deserves a full video of its own, but that video is not tonight. Tonight is about what is already happening, and what is already happening is extraordinary enough without adding anything theoretical to it. Part 21. The Pacific is active. Let me give you some numbers, because I think they matter for keeping this story honest. In the 7 days prior to tonight's events, the United States Geological Survey recorded approximately 87 earthquakes globally at magnitude 4.5 or greater, 87 in 1 week. That works out to more than 12 significant seismic events every single day, somewhere on this planet without pause, without rest, without any particular news coverage. Japan registered multiple events across its complex network of subduction zones and volcanic systems. Indonesia saw activity along its volcanic arc, the same arc that has produced some of the most destructive eruptions and earthquakes in recorded human history. Alaska produced several moderate quakes along the Aleutian Island chain, the kind of events that Alaskans who live near the coast have learned to watch with practiced, experienced eyes before deciding whether to move to higher ground. The Ring of Fire, that roughly circular belt of subduction zones, volcanic arcs, and transform fault systems that traces the edges of the Pacific Ocean from New Zealand up through the Philippines, Japan, the Aleutians, down the west coast of North and South America, and across to the Tonga system was doing what the Ring of Fire always does. Moving, grinding, releasing stress in the incremental, relentless way that a geological system operating at the boundary of converging tectonic plates has been doing for tens of millions of years. The Earth, in other words, was being entirely, completely, unremarkably itself. I think it is worth sitting with that for a moment, because one of the ways that online coverage of geological events can mislead people is by presenting individual earthquakes as if they are occurring against a backdrop of normal silence, as if the Earth is usually still, and these events represent departures from a quiet baseline. It is not still. It has never been still. The baseline is not silence. The baseline is 87 magnitude 4.5 or greater earthquakes per week, every week, year after year, whether or not anyone is watching, whether or not the news is covering it, whether or not the event happens under an ocean where nobody lives or directly beneath a populated coastline where every tremor carries stakes. The USGS Shake Map system, the global seismic networks, the university research stations, the oceanographic buoys, they're all picking up this constant background conversation that the planet is having with itself, and most of it never reaches you because most of it should not reach you. A magnitude 4.8 at 500 kilometers depth in a remote stretch of the Western Pacific is not news. It is geology. It belongs in a database, not a headline. So let me be precise about why I am telling you about the Mariana Arc event tonight, because I think the precision matters, and I want to earn your trust rather than just your attention. The Mariana Arc is not uniquely active right now relative to other parts of the global seismic system. Let me say that again clearly, because it is the kind of statement that tends to get lost in coverage that has an incentive to make everything sound exceptional. The Mariana Arc is active in the same way it is almost always active, consistent with its role as one of the most geologically dynamic zones on Earth, yes, but not elevated above its own historical baseline in any dramatic or alarming way based on tonight's single event. If you pulled up the USGS earthquake feed for the Mariana region over the past 30 days, and compared it to any other 30-day window over the past decade, you would find a list that looks broadly similar. Magnitude 4 events, magnitude 5 events, the occasional magnitude 6, distributed across the arc at various depths, the signature of a highly active subduction system doing what highly active subduction systems do. The background noise of the Pacific seismic system is loud. It has always been loud, and most of that noise is, in the most literal and important sense, irrelevant to most people most of the time. This is not a dismissal of the geological reality. It is an acknowledgement of it. The Earth is always active. The question is never whether the Earth is moving. The question is always whether the movement matters for the specific situation of specific people at a specific moment. And here is where tonight becomes genuinely different from the background. What distinguishes tonight's situation from the 87 other seismic events that occurred in the past week is not the magnitude of the Mariana event. A magnitude 5.0 in the Mariana Arc, in isolation, on a quiet weather day, with no approaching storms and no unusual atmospheric loading on the same geography, is background. It would not have made this video. It would not have made any video. It would have been logged, catalogued, added to the dataset, and noted by the researchers who study this system as one more data point in a long and continuous record. What distinguishes it is the overlap, the specific, precise, temporally narrow coincidence of that seismic activity with the strongest storm on Earth, tracking directly over the same inhabited geography in the same hours. Those two facts together create a context that neither fact creates alone, and that context is what we have been examining throughout this video. Think of it this way. The background seismic activity of the Pacific is like the background noise of a city, traffic, construction, the general hum of millions of people and machines operating simultaneously. You tune it out. You have to tune it out, because if you treated every noise as a signal, you would never be able to function. The noise is real, but it is not information. It does not tell you anything specific. It is just the cost of living somewhere that has things happening in it. But now imagine that same city background noise on the night when a Category 5 hurricane is making landfall on the same streets. Suddenly the background noise is no longer irrelevant. That construction equipment that was just noise yesterday is now a flooding risk if it blocks a drainage channel. That traffic hum is now an evacuation bottleneck. The background has not changed. The context around it has changed everything about what the background means. The Pacific seismic background has not changed tonight. What has changed is the context. The strongest storm on Earth is bearing down on the same geography where that background is registering. And when background seismic activity overlaps with an atmospheric extreme of this magnitude, over inhabited territory, the word background stops being a reason to look away. It becomes a reason to look more carefully. There is also a probability dimension here that I want to name explicitly. The argument that the Mariana Arc is always seismically active, and therefore tonight's event tells us nothing special, is technically accurate but practically incomplete. Yes, the arc is always active. Yes, magnitude 5 events happen regularly, but the joint probability of a magnitude 5 event occurring in the same window as a Category 5 typhoon tracking over the same island chain is lower than either event occurring independently. Both of those individual events are relatively rare over this specific geography. Their overlap is rarer still. The fact that both systems have activated simultaneously does not tell us the overlap is causal, but it does tell us the overlap is unusual, and unusual overlaps over inhabited territory deserve more attention than their individual components would command separately. The Pacific is always active. That is not a reason for complacency. It is a reason for calibration, the kind of careful, precise calibration that distinguishes meaningful signals from background noise, that identifies the specific situations where the background becomes consequential, and that keeps the focus on what actually matters for the people in the path of what is happening right now. Tonight, the background became consequential at 9:19 p.m. local time, when the National Weather Service in Tian upgraded Sinlaku to Category 5 over the same volcanic island chain, where the seismic system was registering activity, not because the earthquake was extraordinary by the standards of this zone, because the combination was extraordinary by the standards of what 170,000 people are being asked to survive. The Ring of Fire was moving tonight the same way it moves every night. The difference is that tonight, it was moving underneath a storm that has no precedent in the modern record of this geography. And the people living at the intersection of those two facts had no choice but to stay exactly where they were. Part 22. The atmosphere is active too. Let me zoom out for a moment because the story of what is happening over the Marianas tonight does not exist in a vacuum. It exists inside a larger atmospheric picture that has been building for weeks, and that picture has direct consequences for the 170,000 people waiting on those islands right now. While Super Typhoon Sinlaku holds the title of strongest storm on Earth at this moment, the atmosphere as a whole is not in a quiet period, not even close. The United States mainland has been dealing with its own multi-hazard pattern in recent weeks that would, in a slower news cycle, be generating sustained national conversation on its own merits. Severe weather outbreaks have been moving through the Central Plains, the kind of tornado and hail-producing systems that put millions of people in basements and send storm chasers racing across Kansas and Oklahoma with cameras running. Fire weather conditions have been flagged across parts of the Southwest, where low humidity, high winds and drought-stressed vegetation create the conditions under which wildfires move faster than the models predict, and containment becomes a logistical nightmare overnight. Flood watches have been active in Hawaii as a separate Pacific system pushes moisture over the island chain, demonstrating that Sinlaku is not the only atmospheric event currently demanding attention in the Pacific Basin, and that is just the domestic picture. Globally, the pattern of simultaneous geographically dispersed extreme weather events that has characterized the last several years of atmospheric activity appears to be continuing without any sign of letting up. The era of one disaster at a time, if it ever truly existed outside of our organizational assumptions, is not the era we are operating in. Now, I want to be precise about what I am and am not claiming here, because this is the kind of observation that can easily tip into a narrative that the data does not fully support. I am not suggesting that the tornado outbreak in Oklahoma and the fire weather in Arizona and the flood watches in Hawaii and Super Typhoon Sinlaku in the Western Pacific are causally connected to each other. They are not in any direct atmospheric sense. They are geographically separate events driven by distinct weather systems operating under their own dynamics. The jet stream pattern influencing the Central Plains is not the same jet stream pattern steering Sinlaku. The moisture anomaly driving Hawaiian flooding is not the same oceanic heat reservoir that powered the typhoon to Category 5. These are separate stories happening simultaneously, not one story with multiple chapters. What they share is not a physical connection. What they share is a resource connection. The resources available to respond to Super Typhoon Sinlaku, the federal emergency management personnel, the pre-positioned supplies, the logistical infrastructure, the political attention of the officials who direct and fund disaster response, the media bandwidth that shapes public awareness and political pressure, do not exist in an isolated reserve labelled exclusively for the Marianas. They exist inside a national emergency management system that is right now simultaneously managing multiple active events across different geographies. FEMA does not have a separate budget for each disaster that occurs independently of what else is happening. It has a total capacity that gets allocated across concurrent demands. The National Guard assets that might be mobilised for Mariana support are the same National Guard assets that governors on the mainland are evaluating for their own severe weather situations. The Coast Guard and Navy resources that support Pacific Island response operate within a broader operational tempo that reflects everything the military is being asked to do across all theatres simultaneously. This is the dimension of compound stress that almost never makes it into disaster coverage, because it is invisible from the outside. When you watch the news about a hurricane making landfall, you see the storm, you see the damage, you see the response. What you do not see is the spreadsheet somewhere in a federal operations center showing every other active event competing for the same pool of resources, and the quiet, consequential decisions being made about which demands get prioritized when the pool is not deep enough to cover all of them at once. I am not suggesting that federal emergency managers are callous or indifferent to the Marianas. I am suggesting that the structural reality of a national emergency management system operating under simultaneous multi-hazard pressure means that the response to any individual event is shaped by everything else happening at the same time. That is not a policy failure, it is a mathematical reality. And it matters most for the events that are geographically remote, politically underrepresented, and logistically difficult to reach, which describes the Marianas precisely and completely. Sinlaku, viewed through this lens, is not only a compound hazard for the people directly in its path, it is a stress test for a federal response system that is being asked to prioritise among multiple concurrent demands at the exact moment when one of those demands involves US citizens in a location that has historically received less political prioritisation than comparable mainland events. That history is documented. After Typhoon Mawar in 2023, the criticism of response speed and scale was specific and substantiated. The comparison to how a similar event on the mainland would have been handled was not hypothetical grievance. It was a reasonable inference from observable differences in political weight. And political weight, in the American system, flows from representation. Senators make phone calls that move resources. Congressional delegations apply pressure that accelerates federal response. Presidential attention follows where electoral votes are concentrated. The residents of Guam and the CNMI have none of those levers in the same form that mainland Americans have them. Their non-voting delegate in the House cannot cast a vote on the emergency supplemental appropriation that funds the recovery. Their senators do not exist. Their presidential vote does not exist. The political infrastructure that converts disastrous need into disaster response on the mainland is structurally attenuated for territorial Americans, and that attenuation does not disappear just because a Category 5 typhoon is closing in. Now layer onto that the atmospheric context we just discussed. A federal system already managing severe weather on the plains, fire weather in the southwest, and flooding in Hawaii is now being asked to mobilize for a Category 5 typhoon in the Western Pacific simultaneously. Each of those events is legitimate. Each of those events involves American lives and American property. Each of those events is generating its own political pressure from its own representatives. And the Marianas, with their limited political representation and their geographic remoteness, are entering that competition from a structurally disadvantaged position. I want to acknowledge something here that I think is easy to miss when you are focused on the meteorology and the geology. The compound hazard we have been discussing throughout this video, the interaction between the typhoon and the seismic system, the nonlinear amplification of risk, the infrastructure stress test, all of that analysis assumes a response system that is functioning at or near full capacity and directing its full attention to the event. But response systems are not abstract. They are human institutions with finite budgets, finite personnel, finite logistical reach, and finite political will. When those institutions are being pulled in multiple directions simultaneously, the response to any individual event is necessarily shaped by that competition for attention and resources. For the Marianas, the competition is particularly consequential because the supply chain and logistical challenges we discussed earlier mean that response delays are not measured in hours the way they might be for a mainland event. They are measured in days and weeks. A day of delay in pre-positioning supplies before a Category 5 makes landfall is not recoverable after the fact. The window for meaningful pre-event action is narrow, and it closes fast. If the federal system is distributing its pre-event attention and preparation resources across multiple simultaneous demands, the Marianas, at the end of the longest supply chain in the domestic response system, feel that distribution more acutely than anywhere else. There is a version of this story that focuses only on the storm, the track, the intensity, the forecast rainfall, the surge projections. That version is important, and it is being covered. There is another version that focuses only on the geology, the subduction zone, the earthquake, the compound interaction with the typhoon loading. That version is what most of this video has been about. But there is a third version that does not get told often enough, the version about what happens when a remote, underrepresented, logistically isolated US territory faces an unprecedented compound event inside a national response system that is already stretched across multiple simultaneous disasters. That version does not have dramatic satellite imagery or seismic waveforms. It has spreadsheets and phone calls and budget allocations and the quiet structural weight of political representation that 170,000 people do not have in the same form that other Americans take for granted. Tonight, all three versions are true at the same time, over the same islands, above the same people. And the question of which version receives the most federal attention in the next 48 hours is not a meteorological question or a geological question. It is a political one, and the answer to it will shape everything that comes after the storm. Part 23, Space Weather Thread. I want to be upfront about something before we get into this section. There is a version of this part of the video that would be very easy to make and very satisfying to watch. It would go something like this. Not only is the strongest storm on Earth bearing down on US territory at the same time, the ground beneath those islands is seismically active, but the sun itself is contributing to the instability. Solar energy pouring into the upper atmosphere. Electromagnetic forces coupling with fault systems deep in the crust. The heavens and the earth conspiring simultaneously over 170,000 people with nowhere to run. That version would get clicks, it would generate comments, it would feel complete in the way that a good thriller feels complete when all the threads converge at once. I am not going to give you that version. Not because the space weather data is uninteresting, it is actually more interesting than you might expect, but because giving you the dramatic version when the honest version is more nuanced would be a betrayal of exactly what this channel is supposed to do. So let me give you the honest version, in full, and let you decide what to make of it. In the window around tonight's events, the Space Weather Prediction Center, the NOAA facility in Boulder, Colorado, that monitors solar activity and its effects on near-Earth space, reported elevated electron flux at approximately 1,000 particle flux units. Solar wind speeds were measured in the range of 500 to 650 kilometers per second. If those numbers mean nothing to you yet, here is the context. Quiet sun baseline electron flux sits well below 1,000 particle flux units. Solar wind under quiet conditions typically runs somewhere between 350 and 450 kilometers per second. So yes, what the instruments are showing tonight is elevated relative to the quiet time baseline. Something is happening in near-Earth space that is above normal background levels. But here is what it is not. It is not a major geomagnetic storm. The NOAA geomagnetic storm scale runs from G1, which is minor, to G5, which is extreme and capable of causing widespread power grid failures and satellite damage. No G-scale warning of any level has been issued for the current period. The elevated electron flux and slightly elevated solar wind speeds are real, measurable departures from quiet sun conditions, but they sit well below the thresholds that produce the effects most people associate with significant space weather events. No widespread aurora activity is expected at mid-latitudes. Navigation and communication disruptions at the level that would affect emergency operations in the Marianas are not anticipated from the current space weather conditions alone. So in the most operational sense, the sense that matters for the people on Guam and Saipan right now, tonight's space weather is not a direct contributing factor to the compound scenario we have been examining. I want to be clear about that before I tell you why it is still worth discussing. The reason it is worth discussing is a question that sits at one of the genuinely unresolved frontiers of geophysical research. Is there any meaningful physical relationship between space weather activity and seismicity? Can elevated solar wind, elevated particle flux, or elevated geomagnetic activity influence the behavior of fault systems in the crust of the Earth? The short answer, as of the current state of the scientific literature, is we do not know, and the evidence for a meaningful relationship is weak. The proposed mechanism most commonly discussed involves electromagnetic coupling between the ionosphere, the electrically charged upper layer of the atmosphere, and the lithosphere, which is the rigid outer layer of the Earth that includes the crust and uppermost mantle, where earthquakes originate. The idea is that electrical currents induced in the ionosphere by solar wind activity could propagate downward through the atmosphere and into the ground, potentially influencing the stress state of fault systems near their failure threshold. It sounds plausible in the way that many proposed mechanisms sound plausible before you actually try to test them rigorously. The testing has not gone well for this hypothesis. Multiple studies examining the statistical relationship between geomagnetic activity indices and global earthquake frequency have failed to find a convincing signal above the noise. The Earth produces so many earthquakes at so many magnitudes on any given day that finding a genuine correlation against the background of normal seismic activity requires very large datasets and very careful statistical methodology. The studies that have claimed to find correlations have generally not survived rigorous replication attempts. The mechanism remains proposed rather than demonstrated. The scientific community's current consensus position, to the extent that a consensus exists on a question this open, leans towards skepticism about meaningful ionosphere-lithosphere electromagnetic coupling as an earthquake trigger at the scales we're discussing. There are minority voices in the research community who disagree, and I want to acknowledge them fairly rather than pretending the question is completely settled. Some researchers, particularly in Russia and in parts of the Asian seismological community, have continued to pursue ionospheric precursor research, the idea that changes in the ionosphere detectable before large earthquakes might reflect upward electromagnetic emissions from stressed rock in the crust. This is different from the solar wind trigger hypothesis, but related in its assumption that the boundary between space weather effects and crustal behaviour is more permeable than mainstream Western seismology currently accepts. Whether this research will eventually produce findings compelling enough to shift the consensus is genuinely unknown. Science has been surprised before. What I can tell you is where the evidence stands right now, tonight, as I am looking at the same space weather data that the Space Weather Prediction Centre is monitoring. Elevated electron flux at approximately 1,000 particle flux units, solar wind at 500 to 650 km per second, real departures from quiet sun baseline, not a geomagnetic storm, not a direct operational hazard, not a confirmed contributing factor to the seismic activity in the Mariana Arc or to the compound scenario unfolding over those islands. But here is the thing that I find genuinely interesting about this, and why I think it belongs in this video, even at the honest, careful, non-dramatic level I am presenting it. Tonight is a night with an unusual number of variables elevated above their baseline simultaneously. The atmosphere is at its most extreme expression over the Marianas Category 5, the strongest storm on Earth. The geological system beneath those islands registered activity in the same window. And the space weather instruments are showing readings above quiet sun baseline at the same time. None of those three facts, in isolation, is extraordinary. Category 5 typhoons happen. Mariana Arc earthquakes happen. Elevated solar wind happens. What is unusual is the temporal coincidence of all three being above baseline at the same moment over the same geography. Is that coincidence meaningful? Does it represent physical coupling between systems that we do not fully understand? Or is it exactly what you would expect to find if you looked hard enough at any arbitrary window of time, some collection of variables above baseline, some below, the pattern only appearing significant because we are primed to look for it after identifying two events that are genuinely significant? That question is one that current science cannot answer definitively, and I think that honest uncertainty is more valuable to you than a confident narrative in either direction. The confident narrative that says space weather is driving seismicity tonight is not supported by the evidence. The confident narrative that says space weather is completely irrelevant and the ionosphere-lithosphere boundary is perfectly impermeable is also ahead of what the research has actually established. What we have is a third option, which is less satisfying but more accurate. We have elevated readings on three separate instrument systems, atmospheric, seismic and solar, occurring in the same window over the same geography, with the causal relationships between them either absent, undetectable at current instrument sensitivity, or operating through mechanisms we have not yet characterized well enough to confirm or rule out. What that adds to our picture tonight is not a new threat. It is not a new mechanism to worry about on top of the typhoon and the geological activity. What it adds is another layer of uncertainty in a situation that already has more uncertainty than the official forecasts are designed to convey. And in a compound hazard scenario over 170,000 people with no evacuation option, uncertainty is not a neutral quantity. Uncertainty is the space between what we know and what we have planned for. And that space tonight is wider than any single instrument system would suggest on its own. The sun is doing something above baseline. The ground moved below baseline. The sky is at its most extreme above those islands. Whether those three facts are connected or coincidental is a question I cannot answer. What I can tell you is that all three are true, right now, simultaneously, and the people underneath them deserve to have all three taken seriously. Part 24. Final Synthesis. Let me rebuild the full picture one piece at a time, because you deserve to hold it all at once before we finish. April 12th, 9:19 p.m. National Weather Service Tian. Super Typhoon Sinlaku upgraded to Category 5, the strongest storm anywhere on Earth at this moment, tracking directly toward Guam, Saipan, Tinian and Rota. Approximately 170,000 American citizens on those islands. No evacuation possible. Typhoon force winds inbound within hours. Seas building to 30 feet. Flash flooding imminent across all major islands. Within hours of that upgrade, a magnitude 5.0 earthquake registered by the USGS near Pagan Island in the northern Mariana Islands. Depth 226 kilometers. Same volcanic island chain, same geological arc, same window of time. The storm is not an ordinary Category 5. It intensified from a tropical depression to peak intensity in approximately 96 hours, crossing the rapid intensification threshold multiple times. It is arriving in April, an off-season anomaly enabled by a Western Pacific warm pool that has grown thicker and more energetic under conditions that researchers have linked to decadal patterns of ocean heat accumulation. The storm did not stall, did not weaken, did not encounter any of the self-limiting mechanisms that reduce intensity before landfall. It is arriving intact. The earthquake is not an isolated geological event. It occurred within the Wadati-Benioff zone of the deepest subduction system on Earth, a system whose surface expression is the volcanic island chain that the typhoon is targeting. The same old, cold, brittle Pacific plate that produces the Mariana Trench also produces the islands. The seismicity of that system is the seismicity of the ground under every building and shelter on Guam and Saipan. The compound interaction of these two systems, atmospheric extreme and geological activity, simultaneous same geography, creates a risk scenario that existing emergency planning frameworks were not designed to address: nonlinear amplification of structural damage, rainfall saturation lowering the trigger threshold for seismically induced slope failure, coastal infrastructure undermined from above and potentially from below. Emergency response frozen by the typhoon at the exact moment any secondary geological event would require response. Supply chains already fragile, now facing compound demand in a supply-limited environment. And underneath all of this, 170,000 Americans who cannot leave, served by a federal response system that has historically prioritized mainland events over territorial ones, living in the political structure of territories that gives them no Senate representation and no presidential vote. Here is what I want you to carry out of this. We have built extraordinary systems for understanding the individual components of natural disasters. The track models for Sinlaku are being updated every 6 hours with some of the most sophisticated atmospheric modelling on Earth. The seismic networks monitoring the Mariana Arc are sensitive enough to detect events that humans cannot feel. The satellite technology giving us real-time imagery of the storm's structure would have been considered science fiction a generation ago. What we have not built, not in emergency planning, not in building codes, not in response frameworks, not in political representation for those most at risk, is an architecture for understanding what happens when these systems interact. When the atmosphere and the geology speak to each other over the same ground, in the same hours, faster than our single hazard frameworks can turn to face them, 170,000 people are about to find out whether the gap between what we know and what we have planned for is a gap they can survive. We've built systems to track storms. We've built systems to monitor earthquakes. We've built systems to measure the heat content of oceans and the solar wind from the sun and the electron flux in the ionosphere. But we have never truly tested what happens when all of those systems peak simultaneously, over the same people, on the same islands, on the same night. Tonight is that test.